So now let's start with Federica Beduini.
Okay, thank you. Can you hear me? Yes. Okay, thank you and welcome. So please do not be scared by the title of my talk, even if you're not in quantum physics, because what I'm trying to convey you in this talk, it's like what I did in my research. And what I did in my research mainly tries to answer a question that is kind of general in science. So it's like what happens when you have a complex system, and then what happens to the elementary particles in that system that is very complex. And just let me give you an example so that it's maybe much easier. This is an example that is from a completely unrelated field. So that little bird is a starling. And these kind of birds like to gather in large flocks like the one that are in the picture above. And they like to gather in these flocks in these kind of shapes morph in one another. And it's an amazing show to see and watch. But the thing is that also you can ask yourself, what happens? So how all these birds correlate, interact between themselves, forming this amazing shape. So how does it happen? And so some people did it, and the way you have to approach this thing is that you have to look at the global shape and then watch with an instrument like the binocular to the individual birds and see what happens, what they do. Some people in Rome that work in complex physics, they did it. And they understood that the interaction between the birds, it's really like what happens between magnets. And this kind of approach, it's practically the same that we did in our group, but looking at something that is related to quantum physics. So the idea is that we have a macroscopic state that is the equivalent of the flock of birds. Then we will look at it with some instrument that we have to identify which one it is to see what happens to the microscopic elements in this global state. And maybe if we cannot make sense of what we are seeing, maybe we need some analog system to see and to explain what is happening. So one of the interesting things that involve a lot of particles in quantum physics is atomic spin squeezing. So you can imagine that each atom is like a compass, and the direction in which the compass aligns, we call it the atomic spin. And then if you sum all the spins of all the atoms, you get the global spin of all the clouds. And then you can measure this, but the problem is that you can always have an error. And no, it doesn't matter how precise you have, there's like a limit that is posed by classical physics that you cannot go under. So you will have always this error. But the thing is that you can do some black magic with quantum physics, and then you can reduce this error below the classical limit, and that is squeezing. The thing is that also people ask themselves what happens then to the single particles in the ensemble, because it's something that involves the error of the global spin, so it means that it involves all the particles together. And so theorists try to answer this question, and they say that there is something interesting between the microscopic elements of the cloud, and it's entanglement. Now I don't have time to explain you what it is, but let me just say that the entanglement is like at the basic of all the interesting application of quantum physics, like quantum computing or quantum communication, quantum cryptography, that maybe you have heard about it. And then in our group, so the problem is that there is no instrument nowadays to look at the single atoms in the cloud. And so what we think about in our group was that there is a system that can be described mathematically in the same way as the spin of the atoms. And that is the polarization of light. So what we did in our group was to reverse the situation. So we produced a state where the thing that we squeeze is not the spin of the atoms, but the polarization of light. And this we can do it in the lab. And also we can build an instrument, this is one image of the lab, that can look at the single elements of the state of light that are the photons and look at their microscopic correlation. And so we were able to see at the end directly for the first time some microscopic entanglement in a global state like the squeeze state. So thanks for your attention. And also I would like to thank all the people that helped me get into these results.